All right. Welcome to. Um, Hold on, 2 seconds. I just need to mute this. Okay, mute. Okay, welcome to the lesson on acids, bases, and salts, which is the beginning of the new unit that we're about to start. If you're here, just say hi on the sidebar, just so I know. I'm allowing you all to watch me as I, record my lesson that I'm going to be sharing later on. So if you have any questions as I'm going through stuff, feel free to just, ask questions as I go so that I can get a feedback as to if you're understanding something or you're not understanding. Hi, Dylan. If you are listening right now, just give me the thumbs up that you're not hearing double. I'm pretty sure that I muted myself, that you're not hearing double, that you can hear me, that everything is good, that there's audio and you're able to see what's going on. We need to talk today about acids, bases, and salts, which is the work of this gentleman, savant Arrhenius. He was a Swedish chemist in the 1800s, and he is responsible for many things, one of them being this concept of acids, bases, and salts. And at first glance, it may seem like, these three things are not related to each other. They're kind of like a dumping ground, like all these like random three things that are, kind of put together in a unit. But if you truly understand chemistry, the reason why they're grouped together in the unit that they are is because these three compounds these three compounds or these three chemical species, they have a property to them that is an underlying theme as to why they're all grouped together. The reason why acids, bases, and salts are all grouped together, and if I had to rename this unit, like it's, the name comes from the Regents curriculum, if I had to rename this unit, I would actually name this unit Electrolyte Chemistry. This is all about the chemistry of electrolytes. And it is something that we have spoken about, briefly before in the unit of bonding. When we learned about ionic compounds, we just briefly mentioned the word electrolyte. And anybody who has ever played sports before, you probably have heard of an electrolyte. You usually drink something like Gatorade whenever you work out. Or, if you've ever been sick before as a child, maybe your parents gave you Pedialyte, which is the pediatric version of Gatorade or an electrolyte, and you drink it when you're sick. And a lot of people think, oh, we drink Gatorade or we drink Pedialyte because we need energy. And it's an energy drink. And that is actually the farthest thing from the truth. You're not drinking Gatorade for energy. You're not drinking Pedialyte for energy. You're drinking both of those things because they are an electrolyte solution. And electrolyte solutions are very, very unique because electrolytes have the ability to conduct electricity in the aqueous form. So when you drink Gatorade or you drink Pedialyte, the reason why you're doing that is because you are replenishing your body's ability in order to conduct electricity in the aqueous form. And some of you are like, that's crazy. Why would I ever want to conduct electricity in the aqueous form? Like I'm going to electrocute myself. Like why would I want to do that? The reality is that you definitely need electrolytes inside of the human body because there is one body system that runs on electricity, and if you don't have electrolytes inside of your body, then your body is not able to send electrical messages. The nervous system is running entirely on the fact that you can conduct electrical messages quickly from the brain and the spinal cord to other parts of your body. If you don't have electrolytes in your body, you're not able to conduct electricity, and you wouldn't be able to send electrical messages to your muscles to move. You wouldn't be able to send electrical messages to your digestive system subconsciously to digest your food. You wouldn't be able to send electrical messages to the heart, which runs on the constant input of electrical energy. There is an area in the heart called the bundle of His, which is responsible for receiving electrical messages. It's the pacemaker of the heart. And every time your heart beats, it's because the brain is sending an electrical zap to the heart saying beat. And then the bundle His is like, oh, electricity, and goes, oh, beat. And if you don't receive that electrical message, then your heart stops beating. You need electrolytes in your body because they are responsible for conducting electricity when the aqueous form. The other thing I just want to throw out there is that there was you constantly need to have a supply of electrolytes in your body to conduct this electricity when you're playing sports. Like, not to sound creepy, gross, or disgusting, but like when you play sports, like if you sweat, and I don't know if any of you ever like tasted sweat recently. I mean, I know it just kind of happens when you're like working out, like maybe you just, feel a little sweat in your, I don't know. If you ever tasted sweat before, it tastes salty. Like that's That is the reason why they are dumped into this unit. Salts are a form of electrolytes. When you work out, you're losing salt in your sweat, so you drink Gatorade in order to replace the salt that was lost. When you are sick, you drink Gatorade. When you're sick and you're a child, you drink Pedialyte. And the reason why you're doing that is to replace any sort of salts that are being removed in your body when you have a high fever, you're sweating. Or if you have some sort of gastrointestinal problem, you're vomiting or you have diarrhea, like you're losing salt from the body. And that needs to be replaced, otherwise you are not able to conduct electricity, and that's a problem. A couple of years ago, I feel like, I don't even know how many years ago because I've told this story for a while now, but there was a college where the fraternities and sororities were told that they were no longer allowed to haze their pledges and they were not allowed to drink alcohol on campus. So the fraternities and the sororities were like, that's cool, we're just going to make our pledges drink gallons of distilled water instead because, like, haha, like nobody can die from water. If you're drinking distilled water, you're drinking pure distilled water. And if you put pure distilled water into the body, there are no dissolved ions in pure distilled water. So these pledges were drinking gallons and gallons of pure distilled water. And, a couple hours later, some of their pledges went into cardiac arrest. Their hearts stopped beating. And they were like, we don't understand. Like, all they did was drink water. Well, if you drink pure distilled water, you are diluting the amount of electrolytes that are in your bloodstream, which prevents the body from receiving electrical messages. These pledges went into cardiac arrest because they could no longer send electrical messages to the heart to keep the heart beating. Long story short here, electrolytes are really important in biological systems because they are responsible for conducting electricity in the aqueous form, and our entire nervous system relies on it. But electrolyte chemistry is something we talk about in this class because it does not just talk about salts. In this class, we're going to dive a little bit deeper and talk about acids and bases, which are also fitting the criteria or fitting the category of electrolytes. In this story today, I want to talk to you about what does it actually mean to be an electrolyte. So here's like my aim, like my things I want to talk to you about today. A little bulleted list for you. Here's where we need to go today. I'm going to shrink this down just a little bit. Here's where I need to go today. I need to talk to you. Well, what does it mean to be an electrolyte? Which is kind of like that first line that I have going on up there. What does it mean to be electrolyte? How does something become an electrolyte? Like, what makes it an electrolyte? And then what properties do electrolytes have? That's where I need to take you today. I know you read in the review book about acids and bases and, salts very briefly, and they do a good job at kind of highlighting the definitions of acids and bases, but I feel like the one thing that's really missing from the review book reading was this whole concept of electrolytes. Like, what does that mean? Like, where'd that come from? Which means I gotta go back and I need to review with you a few things that you have seen before in this class, and things that are important that are going to lead us into that foundation of, well, what does it mean to actually be an electrolyte? In the beginning of the year, we learned about, I'm going to go bolded list, but I'm going to shrink it down. We learned about this word salt, and the word salt is a synonym that we use for anything that is ionic. So in the beginning of the year, I know I said to you, oh, like salt, and everyone's like, oh, NaCl, like the white stuff you put on food. I'm like, yes, that is a type of salt. If I were to say to you as an average normal human being, like, hey, go get the salt, you're gonna bring me the white stuff that you put on food. However, if you say to a chemist, like, go get me the salt, we're gonna be like, wait, what are you talking about? Like, that could mean anything. Like, there are like hundreds and thousands of different types of salts that you could possibly be talking about, and 99.9% of them you don't want to put on your food because it's gonna kill you. You don't, when you say to a chemist the word salt, we are using the word, we're associating that with ionic, and anything ionic to a chemist is considered a salt. So those of you that are watching on the stream, if you're watching, I'm just going to pause for a minute. If you are watching this and you're watching this not live, I want you to take a minute and just kind of jot down a few things that you would associate with the word salt. Like, what, not salt, the word ionic. There are so many things at this point in the year that should be word associations and triggers that are coming to your mind when you hear the word ionic. If you're watching on the stream, I know there's a handful of you here, which is great. You're watching me record. If you want to throw down some things, like, interactively, go ahead. Otherwise, I'm going to pause for a minute and pretend, people are writing stuff down. And then I'm going to go through some stuff with you. If you're here, start throwing out some things that you would associate with the word ionic. I'm going to pause for a minute. Okay, so things you should be associating with nonmetals, ionic compounds at this point, is that you should have a metal and a nonmetal in your compound. Okay, other things that you could be associating here, doesn't have to be metal, nonmetal. We could substitute a polyatomic ion in either position, so polyatomic ion and nonmetal, that would work. It could be, oh boy, it could be a metal and a polyatomic ion. That would work too, as long as the polyatomic ion I'm substituting has a negative charge in the back position. If the polyatomic ion has a positive charge, then it needs to be in the front position. Okay, the next thing that I'm going to throw down here with is that it could be a polyatomic ion and another polyatomic ion, like two of them together, as long as they are positive and negative in the appropriate positions. And the fact that we are talking about metal, nonmetal, means that we have a full-on transfer of custody in the valence. So transfer of valence electrons. And really importantly here is if you were to take a look at this in some sort of picture, because there is a transfer of electrons, we have full-on brackets and we have full-on charges, which is where the story begins today. We have brackets and charges. So, in order for you to be an electrolyte, you need to conduct electricity in, the key word here is the aqueous form. And the word aqueous means that we are physically mixing and fully dissolving into water. So I'm going to start my story off with, I have a container. Here's my artistic sketch of beaker. And in that artistic sketch of beaker, I have a whole bunch of water. Okay, Lewis dot diagram of water. Okay, that's a horrible O. Okay, perpendicular to the central atom. That's terrible, two dots. Perpendicular to the central atom. I have my two hydrogens. And if I were to do the famous book and hot dog test, this does not pass book. It does not pass hot dog. This thing is asymmetrical. Let's shrink you down. Okay, this thing is asymmetrical, which means that this thing is polar. And if water is polar, it must have dipoles on it. And when we go to assign dipoles, I check out reference table S. Otherwise you can be a nerd like me and have these things committed to memory. Oxygen's electronegativity is 3.4. Hydrogen is 2.2. This hydrogen is 2.2. And oxygen is more electronegative, which makes the oxygen the kind of negative side. And the hydrogens are kind of positive. Okay. Let's say that I am going to take the famous salt that everybody talks about, NaCl, and I were to dump this NaCl in the solid form into this water. We're going to start off by doing a little sketchy sketch with some brackets and charges. The sodium, oh boy. Hold on. Oh, okay. Hold on. Hello? Hi, I'm currently recording my lesson to YouTube. Can I call you back? Okay. All right, bye. Sorry about that. Okay. All right, so I can't do this anymore. Okay, sodium has 1 electron in the valence. And chlorine has 7 in the valence. 1, 2, 3, 4, 5, 6, 7. Sodium and chlorine see each other and it's a match made in chemistry heaven. The sodium's like, I really don't want this valence electrons. Chlorine's all like, awesome, I really want it to satisfy my valence. And the valence has changed, so this guy gets a bracket. And this guy gets a bracket because his valence has changed. And now I have sodium, who's +1, and chlorine, who is -1. Artistic sketch of what just went on here. This is the Lewis dot diagram for something like sodium chloride. And I'm going to group this entire thing. Group. Awesome. I'm going to shrink this guy down. And I'm going to dump this compound into the water. For the sake of cleaning, let's get rid of these numbers. Let's get rid of these lines. Let's get rid of that number. Okay, and let's put in the dipole, which is delta negative. And let's group this guy. Group, shrink. Awesome. And let's put them in the same container. Now, what you need to realize that in a container of water, you never have just like one of these waters. You're going to have like, hi, Savant. You're back. Okay. You're not going to just have one of these waters. You're going to have like many of these waters that are hanging out in this container, and it's the flying water monkey effect, where I know we talked about this right before we went on coronation, where you have all of these waters that are hanging out in physical space, in this container, and there's going to be a whole lot more water than there is sodium chloride when I make this aqueous solution. When the sodium and the chlorine that are bonded together, match made in chemistry heaven, when they get put into the water, all of these waters are like, oh my gosh, that is the hottest piece of sodium chloride I have ever seen. The oxygens, which carry their little negative charge, they find the sodium physically attractive. Like this one's attracted, and that one's attracted, and this one's attracted. Keep in mind, I only drew 4 water molecules. There's really like 6.02 times 10 to the 23rd of them in there, so you can really imagine how complicated this gets. And at the same time, don't feel bad for chlorine. Chlorine carrying the negative charge, the hydrogen tails are all like, whoa, that is the hottest piece of chlorine I have ever seen. You're attractive, you're attractive, you're attractive. There are so many physical forces of physical attraction that go on. All of these water molecules swarm the sodium chloride, and there is a force of physical attraction. Now, the next thing that happens in this little story, and for the sake of keeping this nice and clean, and you can understand and you can draw with me as you're doing this, when the sodium chloride goes into this container, the sodium who's carrying the positive, this is really ugly. Let's do this. Let's do this right. Yeah, that's way better. Okay. The sodium chloride no, I'm just going to write that one. That's where I draw the line. Okay, the sodium who's carrying the positive charge, when the flying water monkeys come in, they all swarm with their little oxygen heads, which are negative. And for the sake of just keeping this simple, I'm not going to draw all the hydrogens. The little heads are the oxygen, they swarm, and they're like, that is the hottest piece of sodium we've ever seen, because sodium has a bracket. And sodium has a +1 charge. And all those little heads are negative. And the water, these little flying water monkeys, they get in between the sodium and the chlorine. And the flying water monkeys are going to pull the sodium. I don't want that to happen. The flying water monkeys are going to pull the sodium away from the chlorine. And don't feel bad, because at the same exact time, the chlorine, who's carrying its negative charge and its bracket, the little flying water monkeys come in, but they come in like tails first. They're like da 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 da, like butt first coming in, and their little tails are positive. And those little tails are going to wedge themselves in between the sodium and the chlorine. And when that happens, they pull the sodium away from the chlorine. And we have this process called dissociation, which was one of the things that we talked about right before we went on coronation. It's so not a vacation. Right before we left school, this process of splitting into ions, which is exactly what just happened here, this like dotted pink arrow, this is what we refer to as an ionic dissociation. So I'm going to shrink this down. This is dissociation. When an ionic substance, When an ionic substance splits, when an ionic substance is physically, I really can't type, physically split into its ions by water. And this is kind of where I left you the other day when we were still in class. We just talked about dissociation. But here's the bigger message and the bigger take-home idea of why this is so important. When ionic substances physically split into its ions in water, the ions are now free to move around in the solution. I need to go back here. I'm going to extend the page. The definition of electricity is the movement of charged particles. When charged particles are allowed to move around, they can create a current. Before, when this sodium and this chlorine were together and they were in the solid form, they were locked in place. They really could not go anywhere. If you were to, take an entire box of salt into a bathtub with you, like dry salt, you're sitting in a bathtub and someone were to, come along and drop a curling iron in, you're not going to die because it is a solid piece of sodium chloride. There's no movement going on. You can hold a box of salt and touch something electrical and you're going to be totally fine. However, if you have ever, seen weather advisories and they tell you do not go swimming in the middle of a thunderstorm, in the ocean, that's a terrible idea. The massive difference is that in the ocean, the sodium and the chloride, they've split into their ions, and in the ocean you have sodium, which is free to move, you have chlorine, which is free to move, and you can only conduct electricity when there is a movement of charged particles. These particles are charged, but they're not free to move. When you allow them to dissociate, they are now free to move around in the solution, which allows the ability to conduct electricity, aka an electrolyte. I'm going to pause for a minute because this is the massive, massive take-home message. This concept of dissociation and having free ions that are allowed to move around in a solution. That is what makes something an electrolyte. I'm just going to pause for 1 second. I'm just going to take a look at the sidebar if you're watching. If you're watching, give me a thumbs up. We're in a good place. Otherwise, I'm going to start moving on. If there's no questions, I'm going to start moving on to the next component, which is the salt component. Okay, so the word salt means anything ionic. Let's talk about bases. This is the table of common bases. This is reference table L from your reference table. And for the sake of making a point tonight, we're going to ignore this guy. He's an exception to a rule. And today is not the day for exceptions. Not today. I want you to take a look at what's going on here. You have sodium hydroxide, you have potassium hydroxide, you have calcium hydroxide. Like, all of these end in hydroxide, which is one of the things that distinguish a base according to this gentleman named Arrhenius. Let's go over here. Oh no. Okay, copy. According to this guy, Arrhenius, bases have to have this component here, hydroxide. According to Arrhenius, a base must contain hydroxide. So I'm going to go over here for a minute. I'm going to shrink you down, and I'm going to bullet the list. Bases are substances that contain hydroxide ions. It's been a really long day. I'm so sorry about the typing and the spelling, although it really shouldn't surprise you. I never could type or spell before Corona. Okay, so they have to contain hydroxide ions. Now, the next thing that hopefully you're picking up on is that not only do they have hydroxides, but if you start taking a look at what else we have here, we have something like sodium. We have something like potassium. We have something like calcium. I'm going to go to a reference table for a minute, and I'm going to, oh, let's go to this. Let's get a periodic table up in here. I don't need the whole, yeah, we'll get the whole periodic table. Let's get a periodic table. New. All right, this is going to be massive. A little shrinky, shrinky. Come on. Let's rotate you. Diagonal periodic table. Okay, so according to this list that we have going on here, let's actually copy and paste you. Copy, paste. Okay, let's put this. Okay. Group. Okay. And I didn't mean to over highlight that. Ungroup. Okay, so we have sodium, we have potassium, and we have calcium. Just to do a little highlighting to make sure that we are on the same page here and we know where we can find these things. Here's sodium, here's calcium, and here's potassium. Okay, something I want you to realize, no matter where these things are, these are just some. These are not all of the bases, but these are just examples of bases. If I were to cut this periodic table on the green staircase, Biggie, Smalls, and Tupac, shoot, gangsters, this is the non-metallic the metalloid staircase, which means over here, this is where I have all my non-metals. Over here is where I have all my metals. It is really interesting because everything that's in this first position on this table, according to Arrhenius, should be metals. So they contain hydroxide ions, and they start with a metal, and if you have metal, so let me just write this out here, metal bonded to a hydroxide ion, Doesn't that kind of sound like what we have going on here? I have a metal bonded to a polyatomic ion. It's the same exact idea. According to Arrhenius, a base is just a specific ionic salt. Bases are specific ionic salts that contain hydroxide ions in the negative position, and they contain a metal in the first position. And if I had to give you a formula for this, it should be metal bonded to a hydroxide ion. Now, the reason why I took the time to have the whole discussion with you in the beginning about salts is because if you wrapped your mind around this, the only difference between the first PowerPoint slide and this slide is that instead of it being NaCl, paste, instead of this being NaCl that is dissociating, this is not a chlorine. We would substitute this chlorine with a hydroxide ion. It's the same exact concept. It doesn't matter what's in here. It just matters that we have brackets and charges, and those charges can be pulled apart by the water because the brackets have charges and the waters have charges. When this is pulled apart, according to Arrhenius, the reason why bases are bases is because they dissociate. And when they dissociate, they split into ions, and the ions are now free to move around. They can conduct electricity. But according to Arrhenius, my smartboard file is just freezing for a more minute. According to Arrhenius, there is a very, very specific ion that is going to be generated when you have a base. According to the salt slide, which I can't flip right now, according to the salt slide, it's anything ionic, so anything in these brackets and charges would fly when you are a salt. However, when you are a specific base, not only are you ionic, not only do you have the brackets and charges, but you very specifically have this ion right here, which is the ion of bases. According to Arrhenius, when these things dissociate, they have the ability to conduct electricity. The ions are free to move around in solution. But according to Arrhenius, the ions of bases are hydroxide ions. It's a very, very specific ion. When you have this very, very specific ion, that solution is going to have basic properties, which is what you saw in the reading. According to the review book reading that you did, bases are going to have a pH that is greater than 7. So I'm going to go over here. pH of greater than 7. They are going to be what we call caustic, which means that they can degrade the skin, like they're just not cool, you don't want to like hang out with them, and they are usually slippery to the touch. And the example of that would be something like soap. Soap is a base. We're going to get into more properties, where we'll get into that another time, but these are the basic properties that you saw in the review book. They start talking about this thing called litmus. Bases are going to turn litmus paper blue, and I feel like that's something, litmus paper blue. We're going to get into all the indicators and the litmus paper, but that's a whole nother, lesson for a stream and a whole nother day. The review book does a good job of reviewing and tying everything together, but these are all little things that I'm going to touch on in separate streams, like individually. So that's the deal here. I want you to take a minute, give me the thumbs up on the sidebar to make sure we're in a good place, and then I want to throw down here with acids. According to Arrhenius, in order for you to be an electrolyte, so I'm going to go back over here, they have the ability to conduct electricity in the aqueous form. And the only reason why we're able to do that is because we are dissociating. Like, this is really important. And the reason why things can dissociate is because they have brackets and charges, and water is polar. So there's like these brackets and charges, and water is polar, which allows them to find each other physically attractive. In order for you to have brackets and charges, you need to be ionic to be able to pull these things apart. I want you to take a look at this table for a minute. I want you to look and start telling me, start brainstorming. I'm going to pause for a minute so you can do this. Start brainstorming. I want you to look at what kind of things do you see in common? What kind of generalizations can you make? If you had to define an acid according to what you see on reference table K, what would you go with? Take a minute, start writing, start thinking. I'm going to give you my explanations. If you're watching on the sidebar, now would be a cool time for you to throw down with anything that you're thinking. Otherwise, if you're not watching live, then start writing a few things down that you think would be important if you were trying to define these things. Okay, so the first thing that people are picking up on right now is that they all end with acid. And if this was an honors or this was an AP class, I would be teaching you how to name these things. You're very lucky because you have a reference table that gives you all the names. You are never going to need to name these things. There's something else that hopefully you pick up on in terms of the formula. Okay? Another thing that people are picking up on is that, oh, they're all aqueous. Well, that makes a whole lot of sense because in order for you to be an electrolyte, acids, bases, and salts, let's go over here, acids and bases and salts, they can only conduct electricity in the aqueous form. And the reason why they're conducting electricity in the aqueous form is because we have this dissociation going on. That's important too. If I take a look at this table, these are all aqueous as well. That makes sense. There's something else that hopefully you're picking up on, and it has to do with this. H, 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 H. There's two notations here. We're only going with the notation that starts in H. This is another conversation for another day. Different conversation. I'm going to cross you out as soon as the Smart Notebook opens. As soon as this goes to calligraphy pen, I'm going to cross that out. We're only going to be taking a look at the notations that start with H. The other notations are something that we'll talk about in organic chemistry, which is a whole nother conversation for a whole nother day and probably remotely taught because I don't know when we're going back, but this is a conversation for a different day. Any day now, Smart Notebook. I want to cross that out. So they all start with H, and H is in the first position. Oh, look at that. Already crossed out. H is in the first position. So let's start writing a few things down here. They're all aqueous, they all end in acid, but what's more important to me right now is the fact that all of these start with hydrogen bonded in the first position. ... Now, according to the laws of the periodic table, hydrogen is technically a nonmetal. And if I were to take a look at everything else that's listed here, they're all bonded to nonmetals. Like, nonmetal, this is a package deal, but it has nonmetals, has nonmetals, has nonmetals. Like, oh, they're all bonded to other nonmetals. And if we have two nonmetals, technically, this is covalently bonded because we have two nonmetals. So let's take a minute really quick. We should probably review things that are covalently bonded. I'm going to go over here to do that. So like covalently bonded things. Things that are covalently bonded. Covalently bonded. Let's go bulleted list. Covalently bonded. Two nonmetals. And when two nonmetals get together, they share. And in a picture, if I want to draw sharing, I need lines. And if I have lines, I technically can't dissociate them. And the reason why I can't dissociate them is because they are bonded with a line. They are legit holding hands. They are connected by the valence. Like you're not able to dissociate them. If I go back in this picture, I had no problem dissociating sodium and chlorine because they were bracketed in charge. They were not chemically bound together by the valence. There was a full-on transfer of custody, which gave me the brackets and charges. It allowed me to pull them apart. If I were to look at the sodium hydroxide, same thing. Like, I can pull them apart because there are brackets and charges on it. When I start getting into these things, they're covalently bonded. They're two nonmetals. They're sharing. There's lines. I technically cannot dissociate them. But there is a technicality here. Something that is covalently bonded, I technically can't dissociate them. And that is true 99.9% of the time. This is true. ... But there are always exceptions to rules. And acids are an exception to a rule because of this. The hydrogen that is bonded in the first position. I probably should just highlight that because that would just be a whole lot more clear. The hydrogen is technically, the hydrogen is bonded in the first position, and we need to talk about what that means and why that is so important. Yes, it's covalently bonded. And if anything else was in that first position, it would be covalently bonded to nonmetals sharing lines, and I would not be able to do anything or pull apart or dissociate these. However, because hydrogen is bonded in that first position, that's a game changer. And there's a really important reason why that's a game changer, and as soon as my smart notebook decides it wants to play and unfreeze hydrogen, I'm going to go to this slide for a minute. And according to the laws of the periodic table, anything that's a nonmetal should be on the right-hand side of the staircase. It should be over here. But in the beginning of the year, early on, when we learned about the structure of the periodic table, we learned that hydrogen is over here because hydrogen has 1 in the valence. So like 1 in the valence, like 1 in the valence, 1 in the valence, when it's in group number 1. And everyone's like, excuse me, but like, why is hydrogen in group number 1? But he's like floating in midair. And the answer is, well, technically, hydrogen is floating in midair over here because he behaves like a metal sometimes. But like, he's truly a non-metal, so sometimes people put him over here on periodic tables. He has 1 in the valence, but at the same time, he kind of behaves like things in group 17, but sometimes he behaves like things in group number 1. But sometimes he behaves in group like 17, but sometimes he behaves like group number 1, but most of the time he behaves like a non-metal, except when he's in position number 1 in a compound like this, in position number 1, that is when he behaves most like a metal. And the reason why we're keeping him over here is because he has a valence of 1. He goes in group number 1. He technically could be over here, but this is the time and the place, and the reason why hydrogen is floating in midair. This is the reason all year long he's been hanging out in this corner floating in midair because of how he behaves in compounds that are acidic. That's the whole reason why that was happening. So once again, as soon as my smart notebook file decides it wants to cooperate, I'm going to go back to my acid component in this little recording, and I'm going to jot down some notes with you, and then we're going to call this a day, and then I'm going to get into alternative theories of acids and bases in my next stream. Okay, any day now, smart notebook. Any day. Okay. Okay, so when hydrogen is bonded in the first position, hydrogen is technically a nonmetal. I'm going to go over here and I'm going to add something in. Yep, hydrogen is bonded in the first position. Hydrogen is technically a nonmetal. But when, no caps. But when it is in the first position, it acts like not cats. It acts like a metal. And if it is in the first position, I'm going to go over here for a minute, and I'm going to just sketch this out for you. HCl, which is hydrochloric acid. Technically, this is a nonmetal, and this is a nonmetal. But because this hydrogen is in the first position, it acts more like a metal. So HCl behaves ionically. If I were to draw this, I would technically have a line between the H and the Cl, because technically the valence electrons are shared. But this guy is behaving like a metal, which means that there's a little bit interesting thing going on here. This is going to behave ionically. Behave ionically, even though it is bonded covalently. And it behaves ionically in the sense that when you put this guy in water, the water is able to split the hydrogen into H plus ions. Like water comes along and it's going to weasel its way in between this. And it is then going to pull the chlorine away. And we're able to split these ions. Here's the kicker. In order for you to dissociate, this looks a whole lot like dissociation. However, according to Arrhenius, in order for you to dissociate, you must be something ionic. And technically, acids are not ionic. They're technically bonded covalently. I cannot use the word dissociation here. Dissociation is not the appropriate term. The appropriate term that we use here is we use the word ionization. Ionization, not ionization energy, ionization. Ionization is the process or when acids split into their ions. Acids technically should have no business splitting into ions because acids are technically covalently bonded. However, when you have an acid, and the only reason why this can happen is because, when you have an acid, and the only reason why acids can even do this is because the acids have hydrogen in the first metal position. If they didn't have that hydrogen in the first metal position that is acting like a metal, this would never, ever, ever happen. The only reason why this can happen is because hydrogen is in that first position and it is behaving like a metal. The word dissociation is a very specific word that you can only use for something ionic. When you talk about acids, acids are going to ionize, which is basically just like dissociation. But we can't use the word dissociation because dissociation is only for ionic substances. Ionization, the product is the same, the end result is the same. You're going to have mobile charged ions that are able to conduct electricity, but the process in which this happens is very different than the process in which it happens with dissociation. Dissociation is kind of like getting in your car and like driving to the mall. Like we are going to get to the mall. We're all going to get there, but like you're going to take a different route. I'm going to take a different route. The end destination is exactly the same. We all get to the mall and we do things at the mall. The same idea here. They all have the property of being an electrolyte, but ionic substances go one way. When they are making their electrolytes, they do it through this process of dissociation. Whereas acidic substances are going to use a different route to get there. The end product is exactly the same. These ions are now free to move around and do their business, but the actual mechanism as to how that happens is very different, which is the reason why they had to give it a new name called ionization. The mechanism is way above the Regents level curriculum. If you're in honors, you're in AP, maybe they would talk about that. We will never speak about how ionization happens. All we need to know is that ionic substances and bases dissociate, where acidic substances ionize. You would think ionic substances would ionize. Not how it goes down. I'm so sorry. It's confusing. It is a different method and a different way, but ionic substances will dissociate, whereas acidic substances, those covalently bonded substances with hydrogens in the front position, they're going to ionize. Very different. When they ionize and they have these mobile charged particles, they end up with very specific properties which you saw in the review book. Let's just type this out and then we're going to call this a night. Very specific properties in the review book that you saw, like acids have a pH that is lower than 7. They are corrosive, which means that they cause things to decay and rust and, like oxidize and all that great stuff. They will turn litmus paper red. That is something we'll talk about a different stream, but these are just properties of acids. And the reason why they have those properties is because of this process. Final thing I'm going to throw down with here is Arrhenius comes along, and according to Arrhenius, this guy right here, Arrhenius says that a base has to be ionically bonded with hydroxide ions. That's a thought bubble. That's actually a really horrible speech bubble. Whereas, according to Arrhenius, covalently bonded substances, let's go here, covalently bonded substances acidic substances need to be covalently bonded, but they have to start with hydrogen in the first position, and they will produce H plus ions in solution. Here are those H plus ions. So, summary. I'm going to clean this. What does it mean to be an electrolyte? It means that you have the ability to conduct electricity in the aqueous form because ions are free to move. How does something become an electrolyte? That's an interesting question. If you're an ionic substance, you have to dissociate. If you are a covalent acid, not all covalent substances do this, just covalent acids, you are going to ionize. But this only works if you have H plus in the first position, according to this gentleman named Arrhenius. What properties do electrolytes have? Yeah, I'm gonna modify this. Okay, according to Arrhenius, a salt is an ionic substance that produces ions, mobile ions in solution through dissociation. And then he says that bases are a specific type of ionic substance. I really can't type tonight, and I'm so sorry. Bases are a very, very specific type of ionic substances, just like every square is a rectangle, but not like every rectangle is a square. Every base, according to Arrhenius, needs to be an ionic salt. I just want to keep pointing out here, I keep saying Arrhenius. There's another guy who says something different later on, but according to Arrhenius, it has to be an ionic substance. So a very specific type of ionic substance, and when it dissociates, it produces OH minus ions in solution because of dissociation. The final thing he throws down with here is acids. Acids are a very special type of covalent compound. Because these covalent compounds are sharing and they're not transferring the valence, they should not dissociate. So special type of covalent compound, comma. This very specific type of covalent compound must contain hydrogen in the first position, the metal position. And when these ions split, they are going to produce H plus ions in solution because of ionization. Okay, those of you that were watching my stream live, I know there's a handful of you still left. Just give me a thumbs up. If you have any questions, now would be a great time if you want to ask anything. Otherwise, I'm going to save this, post it on the website, and that's going to be the end of it. Let me know if you have any questions. Okay. Have a wonderful night. And I will see you all. No problem, Dylan. No problem. It was a quiet night. Not a lot of people were watching tonight, but that's fine. I will see you all another time. Okay. Have a wonderful night.